Actually, this is a dual presentation by Dr. Phani from Northwestern University and Mr. Pavan Kumar Polkampally from IIT Kharagpur. But only Dr. Sai Phani would be presenting. But just to know that both of them worked on this presentation on computational modeling of chemical origin of life. So let me take a few minutes to introduce Dr. Sai Phani. Dr. Sai Phani is currently working as a postdoctoral research fellow at McCormick School of Engineering, Northwestern University in the United States. He pursued his PhD in chemical engineering from Indian Institute of Technology at IIT Kharagpur, right? And he has research experience in the computational design of metal oxide-based materials for heterogeneous catalysis, high-performance battery applications, and drug delivery applications, with emphasis on the surface chemistry of different surface exposed facets and site-specific activity. His research interest is also in the field of computational modeling of biomolecular systems. So without further ado, I'd like to introduce and give the screen actually to Dr. Sai Phani to make his presentation. Sir, Dr. Sai Phani, sir.
Good evening, everyone. Today, I'm going to talk about computational modeling of chemical origin of life. And this work we have started in 2018, around when Professor Sudipto Ghosh initiated the work of chemical origin of life through computational pathways. And he brought so many people into a single platform to work on this. And I was also a part of that. Yes, as a human beings, like as a living being, everybody should question, how did life originated on this earth? And like for this past several decades, many scientists and spiritualists and Vedantists are keep on trying to find the answers for this question. So, and okay. Okay, yes. And also in 2005, it was published in Science Journal that 125 questions for which science has no answers. So the first and the foremost question is, how did life originate on this earth? So this is a very fascinating and very interesting and very challenging question to take up for further research. And yeah, like around the globe, many people are trying to find the scientific insights for this question. And yes, so with this question, like we try to model our biomolecular systems to find the stability and feasibility of those systems. Sorry. Yes. Okay, let's compare the materialistic theory of life with the origin of life. Let's take an example of computer. So our computer, our central processing system unit has the motherboard. So the motherboard is made of several diodes, triodes, capacitors, transistors, resistors, and all those stuffs. So these diodes, resistors, and these small semiconductors are made of small components like iron, silicon, carbon, and all those things. But if, like, as we know that these days computers are performing very well because we have high performance computers and we have supercomputers, GPU systems, and all those things. But if we compare it with the real living being, so living being has the consciousness, but computer doesn't have that. And also the living being has the reproducibility. The living being has the capability of reproduction, but the materialistic entity like a computer doesn't have the reproducibility and the consciousness. So moving ahead with this, yes, so coming to the chemical origin of life. So how did what are all the chemical components which exist during the during the primordial earth, like the compounds which were available, like you can say the hydrogen, oxygen, nitrogen, water, and carbon dioxide, ammonia. from which we can make small amino acids, and we can also produce nucleotides and carbohydrates. This is a bottom up approach. As you can start from the small molecules like hydrogen, oxygen, water, and carbon dioxide, and we can produce the biomonomers, amino acids, nucleotides, and carbohydrates, from which we can produce the biopolymers like proteins, oligonucleotides, polysaccharides, which are the building blocks of the protocell. So the protocell has, the cells have proteins, oligonucleotides, polysaccharides are the building blocks. Like if you take a cell is made up of lakhs of all the, like thousands and lakhs of all these proteins, oligonucleotides, polysaccharides, which are built from the simple molecules which existed on the primordial earth. So, like, yeah, many people have been trying to um, uh, make a cell, like, yeah, they, like, many scientists have approached till the stage 3 from stage 1, like by taking the simple molecules and then producing biomonomers. Yes, they have succeeded in producing biomolecules. They are capable of synthesizing biomolecules in the biomonomers in the laboratory. And also, yes, many people could able to produce proteins, oligonucleotides, polysaccharides, but there is a trade-off between the molecular weight of these polymers and the experimental conditions. At what conditions we can produce these materials, and how it could be combined to form a cell. This is a mystery. Like the third step to the fourth step is a very difficult step. Um, which is very challenging for the experimentalists. And also, yes, there were, like, in the, like, people who ever tried in the past, like Nobel laureates like Francis Crick. They have uh, like expressed their dissatisfaction or expressed their concerns about the chemical origin of life. Like, let's see the Francis Crick quote: "Every time I write a paper on the origin of life, I swear I will never write another one, because there is too much speculation running after too few facts. Because there are so many speculations, like how did life originate on this earth? Some people says that it was like based on the small components which existed on this earth, and then by formation of the water and the air. So the mixture of all these things could make a biomonomers and all those things. And also, some people have said that under certain hydrothermal conditions, the some basic chemical components could be generated. And also through meteoric pathway. Yes, there are so many speculations, but there are few facts known by the people, because there are so many things which are still unknown, and still it's a mystery to carry out the origin of life's research. And though I must confess that in spite of this, the subject is so fascinating that I never seem to stick to my resolve. Yes, though he was, like, many times he tried to write an article on that, but still this is so fascinating, because you cannot leave like leave without questioning how did the life originate on this earth. So yes, and also a popular quote from Werner Erber. So the most popular primitive cell may require at least several hundred different specific biological macromolecules. Yes, that's true, because a cell consists of lakhs of biomolecules, and also even proteins. If you take the proteins are built up of so many biomonomers, biopolymers. So how such already quite complex structure may have come together remains a mystery to me. Sorry. So yes, so that is what like Werner Erber said. And also he also said that the possibility of existence of a creator, of God, represents to me a satisfactory solution to this problem. Yes, that is true, because um, if we study the origin of life in only scientific perspective, obviously we may miss some insights, because we may not be end up with whatever we like try for, and whatever the solution which we try for. And I must say that this could be the origin of life research could be carried out, and this question could be um, more put forward, like through both scientific as well as the spiritual pathways. And yeah, yes, that means Vedantic perspectives, both science and Vedantic perspectives. Mm, yes. So as I said, its inability to synthesize in the laboratory, stage 3 to stage 4, it's very difficult. And when it comes to the stage 2 to stage 3, that means biomonomers to the biopolymers, we can, yes, we can produce some biopolymers for like, but there is a trade-off between the molecular weight of the biopolymers and um, the reaction conditions, like at what temperature this could be synthesized, at what pressure this could be synthesized, and at what condition, whether it is in the vacuum or whether it is in the gas phase or whether it is with the solvent phase, because it should match with the understanding of our prebiotic earth. So arguments of feasibility and unfeasibility of various reactions put forward, but no quantitative calculations on feasibility of chemical reactions involved in stage 1 to stage 2, stage 2 to stage 3, and stage 3 to stage 4. Considering these points in mind, we like Professor Sudipto Ghosh instructed us to carry out this research from stage 2 to stage 3. That means by taking the simple biomonomers and to produce the biopolymers and to check how many combinations that we could generate and how it could be differentiated with the molecules which exist. Like there is a hypothesis that there is an existence of RNA type molecules in the prebiotic earth. So like if it is the case, like how it could be, like what arrangement it could take, like by the combination of the three biomonomers. So sorry. Okay, let's talk about the early investigations. In 1953, it was the first experiment conducted by the Stanley Miller and Urey. They synthesized the abiotic amino acid glycine from the mixture of methane, ammonia, and hydrogen under the application of electric discharge, which was the first of its kind in origin of life's research. And yeah, it was like people felt that it was path breaking and it could lead to lead to the many unanswered questions in science. Like after several years, Oro and Kimball in 1960 synthesized adenine from hydrogen cyanide and ammonia. And then later on, Ferris et al. Also synthesized cyanoacetylene from the mixture of methane and nitrogen under the electric discharge. And that the cyanoacetylene, which causes the formation of uracil and the cytosine, because if we see the building blocks of DNA and RNA, they are made of adenine, guanine, cytosine, thymine, and adenine, guanine, uracil, cytosine, and all these things. So from the cyanoacetylene, we can produce uracil and cytosine. But it's a different thing that if we could synthesize the DNA or RNA from the uracil and cytosine. So moving ahead. Yes, moving ahead. So in this bottom-up approach, the blocks which are highlighted in red color so are of our particular interest for our computational investigation. So what we did was we were trying to produce the we were trying to produce the biopolymers from the biomonomers. That means we are moving from stage 2 to stage 3. And if we see the feasibility and stability and thermodynamic feasibility of the formation of biopolymers from the combination of amino acids, nucleotides, carbohydrates. So we can further move from biopolymers to the maybe production of protocells, but that's a different matter. But it is itself moving from stage 2 to stage 3 is itself a big challenging task for most of us. So we are exploring the possible compounds which can form in this soup by thermodynamic analysis, because if you take an example of the chemical soup, so like the chemical soup consists of the three building blocks. One is the nucleotide, and the other one is the ribose sugar, and the other molecule is the phosphate. The combination of phosphate and the ribose sugar and the nucleotide could produce the biopolymers. So as you can select any of these, like cytosine, guanine, adenine, and uracil as well in case of RNA. So here we are exploring possible compounds which can form out of the combination of the three biopolymers by thermodynamic and the kinetic aspects. So like the thermodynamics means like we need to calculate the thermochemistry properties, the free energy formation, and the enthalpies of the formation of these compounds, and the entropies, a change in entropies of these compounds, and compare it with the other feasible structures. So kinetic analysis, that means it comes under the reaction. So which we look at the reaction of between these compounds. So we could do some kinetic analysis by comparing by plotting the reaction energy barrier for different reactions. Yes. So yeah, thermodynamics and kinetics, the stability could be stability of these, I'm sorry, stability of these biopolymers could be produced like could be studied from thermodynamics perspective. So from the free energy of formation of these compounds, like we should do the calculations to get the free energy changes of these combinations at for different configurations under different environmental conditions. As I said, that we must check the vacuum conditions, we must go with the solvent phase, and we must also check with the gas phase, like if the presence of different gases. So how the combination of these three basic biomonomers could arrange themselves and could form a stable bond, like the covalent bonds formed between these combinations, the bond energy. So the bond energy of formation is very important from the thermodynamic perspective. Coming to the kinetics, yes, here we haven't reached up to the kinetics analysis, because first we are looking into the thermodynamic perspective. So first, if we try to evaluate the stability and feasibility, then we can go for certain reactions between these molecules, and then we can calculate the rate constants and the possible rates from which we can evaluate the barrier between different reactions. So that we should be doing in the future. And yes, along with this, we would like to do a permutation and combination analysis. So like, because as the proteins and biomolecule, the proteins and polysaccharides and nucleotides, they have n number of molecules. So to mimic the real the practical situation, so what we would like to do is we take n number of, maybe you can say like some 200 phosphate molecules and 200 ribose sugar molecules and 200 nucleotides, like maybe uracil, guanine, adenine, and combination of those. So how these could form the covalent bonds between the ribose sugar and the nucleotides and with the phosphate group, and how it could and the stability of these interactions could be generated, and how many configurations we could generate out of this, and how it could be compared with the existing like RNA molecules. Like if we want to check the stability of these, so why the existing molecule is stable and why not these? This is the important question that we would like to answer, because why would the other combinations are not stable? It's like, what is the phenomenon? So like, this is what we wanted to uh, question ourselves and to provide reasonable answers for those by using these permutation and combination and further thermochemistry and kinetic analysis, and also to calculate if they are not stable and what makes it stable. That could, like, at what conditions it would be stable and what potential would it require to make it stable. This is what we are interested to study. Yes. So yeah, mm, coming to the computations, we wanted to look into the classical as well as the quantum perspectives. Like classical perspective, like we are interested in performing MD simulations. So classical MD, and few simulations were already conducted by our Dheeraj Dubey from TIFR. So he did some few simulations. It was in 2018. So when Professor Sudipto Ghosh used to monitor us, so we did some unbiased MD simulations and projected the MD trajectory on some suitable collective variable. So here we made a use of Shannon's definition of entropy. And then we try to perform a biased MD simulation along a suitably chosen collective variable. So this approach was undertaken when there is some preconceived intuition regarding the process of undergone. Like for biasing the simulation, we add just biasing potential to the system. So yeah, this classical approach could be best explained by our co-author, our co-researcher, Dheeraj Dubey, um, from which we can calculate the free energies and entropies of different covalent bonds. Yes. So coming to the quantum perspective, plan of our modeling. So from quantum perspective, we start with the reasonable number of phosphates and nucleobases and the ribose sugar molecules. Let's assume that we have three, like we started with three molecules of each, like three phosphates, three nucleobases, and three ribose sugars, and how they interact themselves. Like that means, first, yeah, in a computational perspective, we need to specify the particular type of interaction, because it may not interact in that way if we allow it to be interacted. So first we specify the type of interaction, whether it is the nitrogen of the nucleobase to the carbon of ribose sugar, or maybe oxygen of nucleotide with the carbon of ribose sugar, and the oxygen of phosphate to the carbon of ribose sugar. So these interactions we would specify. We would specify in prior to our computations, and then we see um, the stability of these interactions from our computations. Yes, there are certain bottlenecks. Generating different possibilities cannot be geometrically done, because all kinds of bonds does not occur. To see the feasibility of particular structural stability, we are carrying out DFT studies. Yeah, yes, we performed several computations using density functional theory. So first, we started with two phosphate molecules which are attached at two carbon atoms of ribose sugar, and you can see that the nuclear nitrogen of the nucleobase is attacked to the carbon of one of the carbon atoms of the ribose sugar. And this is the input. The left structure is the left input structure, and the right structure is the optimized structure of our molecule. So this is the total energy of that molecule at that stage, and you can see that the molecules are intact. That means they are interacting. So the interaction is still intact. And further moving ahead, yes, we increased the number of sugar molecules, like two phosphates and two sugar plus one nucleobase. As you can see that the nucleobase, the two sugar molecules is like one sugar molecule at which two carbon atoms are attached to the two phosphate groups, and two sugar molecules are bridged by the nucleobase. As you can see that the nucleobase is just attacked perpendicularly with the two ribose sugar molecules. So these are different combinations which we have explored in DFT computations. So as you can see that these are the 5 unique configurations which were generated for the interaction of a single ribose sugar and the single amino acid and single nucleobase and the single phosphate molecule. Like these are numbered as 1, 2, 3, and 4, 5, like from A to E. So at which like if you see the structure in A, the oxygen of phosphate molecule is interacted with the 1' carbon atom, whereas in B it was attacked to 2', whereas in C it was attacked at 3' carbon atoms, 4', 5'. So like we explored these configurations and we understood that how these are different with each other. Like yes. So we performed thermochemistry calculations, and we found that for different the interaction um, uh, of these 3 biomolecules to form a stable compound with these are the electronic energies, change in electronic energies of these combinations, and these are the entropy of formation, and these are the enthalpy of formation, and these are the entropy of formation of these compounds, followed by this is the delta G. As you can see that there is not appreciable change of delta G from prime 1 to the prime 4 interactions, whereas for prime 5 the energy is increased. That means it achieved higher energy. That means like prime 1 to the prime 4 seems to be reasonable, whereas prime 5 achieved higher energy, because normally the structures which are possible should achieve the lower energies of formation. And further, we need a lot of investigation in these properties, because as you can see that the free energies are positive. Normally, if a stable structure, if the reaction, like if a compound should be thermodynamically feasible, the delta G should be spontaneous. That means it should be negative. So yes, we are still looking into the calculations, and we are trying to improvise our calculations to get the reasonable structures. Yes, coming to the methodology of our computations. So this actually, yes, like some of these blocks have already been discussed when Professor Ghosh was alive. So like afterwards, after doing rigorous analysis, we came to a conclusion that we should follow a systematic protocol. So from which like I formed the I made this flow chart. So the overall idea is to start with the approximate geometry, and then that approximate geometry could be used as an input for geometry optimization and frequency analysis using density functional theory. The main aspect of density functional theory is to choose the proper functional. So as I can say that we can choose any hybrid functional. And also, it's very important to choose basis set. As of now, we will stick to the 631G of D, but we would like to move to the higher level of basis set, so that we could achieve more accurate properties, more accurate results. And these could be the DFT calculations could be performed in both vacuum phase as well as in the solvent phase, and from which we evaluate the thermochemistry properties of the bond stability and the feasibility analysis. And then we would take up the different combinations, and we would like to calculate the external potential, because in order to exist these molecules in the primordial earth, prebiotic earth, so there could be a potential, there could be a strong potential. Like Werner Erber said, that he strongly believed that there is a creator, maybe God. So some supreme personality might be there. So for that, in order to answer that, we could calculate the external potential of these compounds, so that we can say that under certain conditions and under this application of external field, so these materials are stable. Even if you see the Miller experiment, Miller would have not produced the amino acids without the electrical discharge. Yes, there should be some external potential. So that we are interested in finding. So yes, coming to the summary of my talk and summary of our work, these are the key points which I have drawn. So the interaction of phosphate with 1, 2, 3, and 4 primes were found to be energetically and thermodynamically similar. So maybe there is an insignificant change. The interaction with 5 prime is energetically and thermodynamically less stable than the others, because as we saw that the formation, the Gibbs free energy of formation is very high when compared to the other combinations. And the nucleotide can be interacted with ribose sugar via CN, CO, and CC interactions. Yes, these are the three type of bonds which could be formed and which could be explored. We expect that these kind of structures having large number of covalent bonds per atom, which will be more stable than the existing RNA structures. Yeah, which could be, yes, worth exploring. This will be further confirmed by a systematic investigation of geometrical features, thermochemistry properties, and the external potentials. Yes, the future studies. We would like to bring more clarity on the feasibility of bonding based on the systematic DFT studies and the generation of more feasible geometries from permutation and combinations, and to calculate delta G from delta H and delta S of the compounds formed via classical as well as the quantum perspectives. With this, I would like to thank, yes, like this was like as the way we are following yeah, the bottom up approach in the science. This research like was motivated by our beloved Guru Maharaj, Dr. T.D. Singh, His Holiness Bhakti Swarupa Damodara Swami, who instructed different research different research ideas to Professor Sudipto Ghosh. So Professor Sudipto Ghosh, like our, yes, he was a student friendly faculty in IIT, in the whole IIT Kharagpur. And also, like, yeah, we all know, most of us know, and BI knows about Professor Sudipto Ghosh. So Professor Sudip, we must thank Professor Sudipto Ghosh. And also we would like to say that we are badly missing Professor Sudipto Ghosh, because we lost our scientific as well as a good spiritual master. And he was like, when he was like instructing this research to us, we were like, we thought, yes, we are moving in a good direction, and we have a proper direction, and we somebody is there to take after, to look after all these stuffs. So like he was the one who motivated us. It's like top down approach, like from Dr. TD Singh, like it was carried out by Professor Sudipto Ghosh. And Professor Sudipto Ghosh instructed us to carry out this study. And yes, maybe after Professor Sudipto Ghosh left his body from this material world, yes, obviously we are very slow, and we have stopped working on this. But we should, yes, we should get it started again, and we should move in the direction which we would like to move on. So we hope that we would like we would one day we would definitely find the most challenging like we would like to find the answers for the most challenging questions. One of that is the origin of life's research. So with this, I would like to thank all of our co-researchers, Mr. Pavan Kumar Polkampally and Mr. Dheeraj Dubey and Professor Jainarayan Tudu and Mr. Abhinav Sinha and Mrs. Munmun Ghosh, and obviously our beloved Professor Sudipta Ghosh. With this, yes, I'm ending my presentation here, and I would like to take any questions which you have.
Thank you so
And
much, Dr. Sai Phani Kumar, for your presentation. So we'd
yeah,
like to now open up the floor for questions from the participants. And maybe you might want to ask Mr. Pavan Kumar to also participate in the, if he's around. Yeah. So,
yes, he's
yeah,
there. Yeah.
we could. So let's quickly take a look at whose hands are raised. Okay, we have again Nikit Kumar. Nikit Kumar, would like to unmute yourself and ask a question, please.
Yes, hello, sir.
Yeah.
Yes,
Hi.
Yes,
hear
my
you.
question, yes, sir. My question is like, in one of the previous lectures, also one professor told that there are like millions of Rubik cubes, and in that they need some particular assembly for forming the molecule, like as in step 5. And
Yes.
I saw how it is done. Like you have told that prime model 2 is most stable and having least entropy also. So that prime model 2, how it is different from other structures? Can you explain that thing?
Yes, because
Yes, sir.
let me share my screen again. If you see, oh, okay, let me go back. Yes, if you see these interactions, so like the prime one, the phosphate group, like you see in at prime one, there are two molecules interacting to the prime one. One is the oxygen of the phosphate group, okay, and the second one is the nitrogen of the nucleobase. Okay, so these two are interacting with the same atom, they are attacked with the same atom, and they are still aligned, they are still intact. That means there is a feasibility between with this combination. If you see the structure B, so where the prime one carbon atom is bonded with the nitrogen of the nucleobase, whereas the prime two carbon atom was bonded with the oxygen of the phosphate group. Whereas here in C, the prime one was sorry, the prime it was prime one was interacted with the nitrogen of the nucleobase, and prime 3 was interacted with. So these are different combinations. So with these different combinations, if you calculate the thermochemistry properties, you will get different thermochemistry properties. Like you will get different formation energies, like free energies. So like normally if we say the feasibility and stability, this could be answered by the free energy of formation and these are electronic structural calculations. So the electronic energy could also be used as a good measure to answer these questions. So yeah, so these combinations are found feasible because of our computations. And still I already said that these are still under question, that the free energies are positive. So if they are negative, I would confidently say that these structures are definitely feasible, and it could compete with the existing configurations. But this requires a lot of systematic investigation, which could be carried out in the nearest future. Maybe soon we are going to resume these calculations. Yeah, are you clear? Hello, are you clear?
Nikit, is that okay? Is the answer by Dr. Sai Phani? Okay, we've lost him.
Yes, sir. Yes, sir, you are clear. And sir, like that delta G entropy has to be minimum, no, like it has to be negative. So
Yes, yes.
how it is achieved? Like, is it a metastable state, means very unstable state, and how that external field also calculated for getting molecules, like at least in step 4 also.
Yes,
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 sir.
Niket,
Can you elaborate somehow more on this thing?
yes, Niket, I appreciate your
Yes, sir.
questions and your like thinking, because yeah, your thinking is far better than the other people, because yeah,
Okay, thank you, sir.
I'm impressed. Yeah, let me put my answer to this question. So yes, that's why, see, if they are not stable, so that's why we would like to calculate the external potential to find like if we add the external potential to the existing free energies. So like, if you do the computations like DFT, we would have an energy Hamiltonian. So the Hamiltonian has different parts, like it has kinetic energy contribution, it has potential energy contribution, and it has an external potential contribution. So that external potential we would like to calculate. So if we add that external potential, this could be minimized. So what is that external potential? Then we can answer that, okay, if you want to synthesize these combinations, so you require this potential, so this much potential, so this external potential under certain conditions. Yes. So, and this could be, yeah, this could be any of,
Yes,
like,
sir. Okay, thank you for
yeah.
clarification.
Yes, yeah.
Okay, thank you so much for your question, Nikhil, and for your answer, Dr. Sai Phani. We have a
Thank you.
question by Nikhil.
Okay.
Nikhil, could you please unmute yourself and ask the question, please?
Yeah, yeah. Thank you very much, Dr. Sai Phani.
Yeah, yeah.
I have one question. I just want to ask, like, which functional and which basis set you have used for your calculations?
Yes, yes. So so far we have explored B3 LIP, so B3 LYP. So because this is a basic hybrid functional for the density functional theory calculations, and we were stick to the 631 GD. So because our like intention was to first get the reasonable properties and to find the calculations at minimal level of theory. Then we can increase the level of theory. We can go to the advanced levels of theory. Like we can go further to the Minnesota functionals, Minnesota exchange correlation functionals, MO6, MO62X. There are different potentials, and these days they have advanced functionals like M11. So they are very advanced. So we can also explore those once we have a certain basic idea of the behavior of these systems. So
I have
yes.
I have question on your basis set, like, because you have negative phosphate groups, right? So you have negative. So is it not there will be polarizability effect there? So you have to use polarizability functions like
Yes.
631G only. You have to use plus plus functions.
Yes, yes, yes. That's correct. That's correct. So yeah, as I said, these are just for the initial investigation. So
Yeah.
this could be further studied with higher levels of theory, like 631 G of D comma P and 631 plus plus and 6311 plus plus G of D comma P or 3D comma 2F something. Yeah, the different basis sets are available, and also we can go for the zeta potentials. Sorry, zeta.
Yeah.
ZVP, TZVP. Yeah, TZVP.
Yeah,
Yes, we can
correlated
also
functions and
correlated.
zeta
Yes,
function,
yes.
zeta potentials.
Zeta.
Yeah.
Yes, exactly. So we
Okay.
can we could
So
we could
I
use
have
those.
another general question about
Okay.
not very technical. Like, so so how you are planning to do? Like, if you have any thoughts on this biomolecular, you have to take a if you have to take what to take a consideration of the solvent effects, right? So,
Yes.
like, how
Yes.
you are planning to carry out, or what are the things? Like, if you have
Yes.
any plan, you can.
Yeah. For smaller molecules, like if you see the five configurations which we explored for single phosphate and single ribose sugar and the single amino acid, sorry, single phosphate. For these combinations, we can add solvent using polarizable continuum model. and we can do the calculations. And the solvent effects could also be well studied if we take a larger system, like using classical MD, we could do that. Yes.
Yeah.
Yeah.
Yeah. And yeah.
Thank you, Nikhil, for your
Thank you very
question.
much.
Thank you, Dr. Sai Phani.
Yeah. Thank you.
Other questions? If not, I have a question. Maybe could you share with us what are the major assumptions that you had in undertaking this project? This what are the assumptions that you made that form the basis of this project? Because there must be some assumptions that you're making when you
Yes.
undertake this project. Yeah.
Yes, yeah, it's an interesting question because as I said before, because if we leave these biomolecules to interact themselves, so it may be difficult for them to interact and form a suitable complex out of it. So in order to make them intact and to form the complex, so like we specify some interactions a priori to the computations, like the CN interaction, because as I said that, okay, let's attach the phosphate to the first carbon atom and let's see how it goes. And let's attach the nucleobase at one prime carbon and let's see how it goes. If this comes intact, then we move ahead with the computations, or otherwise we would find out the root cause of why these are not intact if they detach from each other. So yeah, we did that because when we tried for three phosphate groups, three ribose sugars, and three nucleobases. So when we tried to make them aligned, so to form the complex, they were not intact because they require they are at the conditions which we did the simulation, they were not stable. So for then we took a single molecules, and then yes, the main assumption which we took for these calculations is like, yes, first let's go and do that vacuum phase calculation. That means there are no environmental effects as of now. So there are no environmental effects. Let's take these three biomonomers and let's see the complex formation out of these three. And after that, like, yeah, like that is what I had shown in my flow chart, that like after doing all these trial and error and different computations, then we realized that we need a systematic protocol to undertake these calculations and to undertake these computations further to get some scientific insights. So like, yes, those are the assumptions which we made, that there are like the Nikhil asked me, like during the computation, why did you use 631 GD? Because it doesn't have any polarizability. Yes, as an initial step, we thought, okay, there are no polarizable effects, there are no effects of the environment, and let's take an ideal system. So that's how we started.
Okay. So how
Yes.
reliable do you think are the in terms of reliability of the data that you've got, the findings? How would you talk assure about the right reliability of the results of the findings?
Yes, like coming to the reliability of the computations, yes. If you see the enthalpies of the formation of these calculations, so like enthalpies of formation, yes, the complex formation is exothermic, because if the process is exothermic, the delta H would be negative. So that is obvious. So that means we are like from enthalpy of formation, I must say that yes, we are moving in a right direction, because but you can see that the interaction with 4 prime is an endothermic process. That means it requires energy to be given to the system. So that means, yeah, we must question that the 4 prime, because if you see, if I get the same means like the like um, um, continuous or drastic change in the thermochemistry properties, then I would have definitely questioned my system that yes, there is something different between these combinations. But I see, yeah, these are reasonable structures to start with. These are reasonable calculations, but we need to look into the delta G, how it is positive and how it could become negative, like at what conditions it could become negative, under the solvent phase, under the gas phase with the presence of different gases, or maybe with the interaction of different molecules. So this could be further investigated. Yes.
For further research, right?
Yeah.
Thank you so much. Are there any more questions for Dr. Sai, Phani? There seems to be, okay, there's one. We can take one quick question from Nikit. Nikit.
Okay.
Please unmute yourself, Nikit.
Yes, sir. Like you have told that materialistic theory of life has both reproducibility and consciousness.
Yes.
Can you tell, like, means through some chemicals, how that consciousness also comes in life? Like consciousness, I meant like ants and small creatures don't have any consciousness, but we humans and complex organisms are very conscious. So how this consciousness, did you do any research or chemical reaction, something on consciousness, how it comes? That is
Yeah.
one question.
Yes, that's true. Like if you want to do the research in consciousness perspective, so first of all, we would we are not successful in producing the protocells. If we are successful in synthesizing
Yes, sir.
the cells, so that we could say that yes, we have a cell and this behaves like this. So at these conditions, it behaves like this. Suppose if you go like you can like it means this is summer, maybe if you sit in front of the AC, so like you feel that yes, yeah, I'm feeling better than when you go out just for a walk. That if you go outside for a walk, you will feel that, oh my god, I'm sweating. So this is very disgusting, like that. If you feel like how you feel, like from where it is coming, how do you feel? So it is based on your consciousness. That means you are based on your consciousness. That means you feel that your cells are behaving as per your consciousness levels. That means whatever your cells inputs to the feeling, that to the, yeah, this may not be the better answer, but consciousness,
Yes, sir.
we should move much forward to study all those things, because we were still in a stage of stage 2 to the stage 3. Like if we go to the stage 3 to the stage 4 of the bottom up approach, we could able to answer consciousness from the scientific perspective. But there are answers from Vedantic perspective, as you might be knowing, or if you don't, then better ask any of our BI
Yes, sir.
people to know the Vedantic perspective of the spirituality, because you have so many books available to read. Yes.
Thank you so much for your question.
Yes,
We
sir.
have
Like
one last
DFT
question.
studies also. Thank you, sir.
Thank you,
Yeah.
Nikit. Thank you, Dr. Sai, Phani. We have one last question in the chat
Okay.
by Vinay, who asks, what sort of external energies are we talking about?
Yes, these are the external energies. It's of electrostatic potentials.
Okay.
Maybe electrostatic interactions. Like if you take, if we calculate the charge of these atoms, like if you see these combinations, these biomonomers consist of oxygen, carbon, nitrogen, hydrogen, and the phosphorus group. So if we calculate the charge distribution of these molecules and the complex formed out of these combinations, we could calculate the external electrostatic potential. So that could answer some of the, like, yeah, few of the questions when it comes to the external potential, because electrostatic potential is also one kind of external potential. Yes.
Okay. I think that the follow-up question is: are those forces natural and always applied?
Uh, yes. Like, if I talk about the Miller and Urey's experiment, it's like Miller and Urey's experiment. They started with the small molecules, and they synthesized the amino acids under certain conditions, under the application of electric discharge. So you need yes, you need to follow some conditions, because naturally we don't know, we don't have proper data for that to compare it with the naturally existing ones. So this, yes, for natural prebiotic environment, the conditions could be um, yes, could be calibrated. Yes.
Okay. Thank you so much for the
Yeah,
answer.
thank you.
Thank you so
Yeah,
much. Let's give a warm applause for Dr. Phani.
yeah, thank you
Thank you
so
so
much.
much. It's a pleasure having you, sir.
Yeah, thank you so much. And I would like to thank Bhaktivedanta Institute for giving me this opportunity to present our research and to talk about the ideas of the instructions which were given by Dr. T.D. Singh to the Professor Sudipta Ghosh, and from Sudipta Ghosh to us. This is a top-down approach. Yeah, thank you.
Thank you very much.